Let's continue with more information on slope and finding equations of lines that are parallel or perpendicular. So let's see what we have here. We have a point, so we know we have an x1 comma y1, and we know that it's parallel to this line. I know that parallel lines have the same slope, but they weren't as nice in this problem. They didn't put it in a form where I could actually get the slope immediately from the equation. So what I need to do is solve for y to get it in a format where I can actually grab the slope. So let's take 3x minus 2y minus 5 and solve it for y. So I'll have negative 2y equal negative 3x plus 5. All I did was drag the 3x over, drag the negative 5 over. I'll finish it up with a division of negative 2. So y is equal to 3 halves x minus 5 halves. This is a much better format for that equation because when it's in that format, I can grab the slope. There's my slope. Now that's the slope of that line. What slope am I going to use for the line I want? Well, it all depends on what they say right here. Since they're parallel, I'm going to use the same slope. When I come over here, I have a point negative 1, 3, and I'll have a slope of 3 halves, and we can very easily fill in the y minus y1 equal m times x minus x1 format. Let me make sure I did this right. Negative 2y, so we'll subtract 3x, add 5, divide by negative 2, and so, yes. So let's fill in our information. Y minus 3 equal to 3 halves times x plus 1 because of the double negative. Well, there's one format, but we could take it and distribute and clean this up a little bit. Get y minus 3 is equal 3 halves x plus 3 halves. Add the 3 on the other side. I'll get 3 halves x plus 3 halves plus 3. And then finishing that up with one more step, 3 halves x, 3 halves plus a 3 is going to be what? Well, I can't add them because I don't have a common denominator, so I need to make this have a denominator of 2, so it'd be like 6 halves. So I'd end up with 3 halves x plus 9 halves. So the two forms for the equation, here and here. Let's look at this last one, find the equation of a line. We want to find a graph. It's passing through a point. Okay, I've got my x1, y1, and it says it's perpendicular to this line. Well, this one's kind of weird because when they say it's perpendicular to something that looks like this, something should pop into our mind about the definition of a line in this format. X equal to negative 4, we should recall, is a vertical line. Well, if I have a vertical line that runs like this, what type of line is going to run perpendicular to it? It's got to be a horizontal line. But those are pretty easy to come up with because a horizontal line is just y equal to a constant. So if I'm trying to find a line perpendicular to a vertical line, the equation is going to be y equal to some constant. The question is, what's the constant? Well, it's whatever is in the y position. And in this case, since it's 6, we're going to have an equation of y equals 6. And that's all we can do with that. It's just a horizontal line that occurs at the y value of 6. That was pretty easy if we recognize vertical and horizontal lines. Let's look at rate of change. That's the last topic for this section. We'll just kind of get started here. Dealing with the average rate of change. And if we go back and look at the beginning of the sheet, when we talked about slope, we talked about it as being the change in y's over the change in x. which is actually a rate of change. How is the graph changing? We saw positive slopes, it was a rising line. Negative slopes, it was a falling line. It's a rate of change. When we're working with equations that are not lines, it's kind of hard to find the rate of change. So let's take a look at that. So let's take a look at a line, this line we may have seen earlier. We can find the slope of this line, which would be the rise over the run, and I can do rise and the run. And let's see, how many units was that? 1, 2, 3, 4, 5, 6, 7. So my rise is 7, and the run is, looks like 6. I may have counted wrong. You might need to check that, but a rise over run, I think, is 7 over 6. Let me see, what is this value? That's a negative 6. Oh, and that's a positive 6. Oops, so it's not. It's 6 over 6. Come on, Kim. It's a rising line, so it's positive, and I just must have messed up my little counting part here. So it should be 6 over 6. Let me count that again. 1, 2, 3, 4, 5, 6. Well, that is at 7. Uh-oh. Alright, you're going to get aggravated with me. That is at the point 7, and that is at the point 6. So I didn't miscount. Okay. The rise is 7, the run is 6. So it's 7 over 6. Okay, anyway, we can find the slope of a line. What if it's not a line? What if we want to find the slope or the change of something like this curve that we have over here? It's kind of like a polynomial function. Well, when we're working with one that's not a line, we want to find the average rate of change between 2 points, and if we draw 2 points, the line that we draw between those 2 points is called a secant line. So I've given you this picture. I want to find the average rate of change. The average rate of change on this one, or the rate of change, was 7/6. Let's pick 2 points over here. Let's say I have this point. It's a nice one that I can, let's say I've got that point. And what's another one I can kind of see? Let's say I've got those 2 points right there. And I want to find what's the rate of change between these 2 points. So I'll connect the dots. And when I connect the dots, I'm forming what we call a secant line. I'm forming a secant line. And the average rate of change for this function between this spot and this spot is going to be the slope of that line. So all we have to do is calculate the slope of the secant line, and that gives us the average rate of change between those 2 points. Well, we know how to calculate, I didn't want to do that. We know how to calculate the slope from our work that we did earlier. So all I would need to do is know this ordered pair and that ordered pair, which we could get from the graph, and we could calculate the slope of that line.